So it's a real pleasure to welcome Jie Shan from Cornell University. Is going to speak about strong correlation physics and semiconductor moiré superlattices. So she has done a lot of excellent work on twisted TMDs, and the floor is yours and the screen is yours. So thank you very much.
Thank you, Frank. Thank you for invitation to this summer school. It's really unfortunate that we cannot all gather in Barcelona, enjoy beach and the beautiful talks. But you know, since we cannot meet in person, this online meeting is you know, a good alternative. So the work I'm going to present today is mostly done by those four gentlemen, Yan Hao Tan, Li Zhongli, Tingxin Li, and Yang Xu. In particular, Yan Hao and Yang are the main contributors. I would also like to thank my long-term collaborator, Kim Fan Mak at Cornell, who co-supervised the group with me. So we are very fortunate to have theoretical support from Alan McDonough at UT Austin, and also Veit Alsa, my colleague at Cornell. We got bulk crystals from Columbia team, you know, Jim Hong and his colleagues, and the boron nitride crystals as everybody else from Japan. Okay, so we've been listening to 17 talks, am I right? Yeah, in this summer school. So I think everybody has already been saturated with Moire superlattices, correlation, this and that. So I would not go into long introduction. I'll just use one slide to recapture what we have learned so far. So imagine we put quantum particles, you know, electron, on a lattice, and lattice spacing is A in this case. So if we consider Coulomb interaction, you can just estimate as E squared over dielectric constant and the distance, right? And because the particles in this periodic structure, they also form electronic bands. You can also estimate the bandwidth of the lowest electronic band as momentum squared divided by 2 times the effective mass of the particle. And the momentum is inversely proportional to the particle spacing. So the parameter that's important for interaction is the ratio of the Coulomb interaction to the kinetic energy or the bandwidth. And in this simple estimate, it goes linearly proportional to the mass and the distance between the particles. So here's the recipe for strong correlation. You know, if you want this ratio to be big, you look for a system with large mass and with large distance A, and that's the low density limit. So for in a solid state system mass, let's say typical something like 10% of electron mass, dielectric constant, you know, for semiconductors, something like 4 or 5. So the ratio can be larger than 1 if the separation is order of 10 nanometers. So this is the new length scale that Moire superlattices introduced. And so here we haven't considered the effective Moire potential. So if you have a deep well, you can confine the states better. And that means you have flat band and large mass. So you can make this W even smaller, and then the correlation will be even stronger. So here's an excellent example from twisted bilayer graphene, this pioneering work from Pavlov's group. and a prediction from Alan McDonough almost 10 years ago. So we have seen this many times, I'm pretty sure. At this twisted angle, the interaction between the two layers is so strong. The Moire potential I mentioned can be big, and then you make a flat band. And we have seen remarkable phenomena such as superconductivity, insulating states, and later development of some topological phases as well. So this is not what I'm going to discuss today. So the graphene system is very magic. The strong correlation physics occurs near or very near the magic angle. That's about 1 degree. And that makes every device its own personality. So if angle is a little bit different, you may see a little bit of different phenomena. And that's interesting from some aspect, but also sort of annoying from reproducibility point of view. And because we start with material with 0 band gap, those flat bands are not very well isolated. So one may ask a question, can we still ask for magic without a magic angle? In other words, can we have a wider range of magic angles? Then you don't need to try extremely hard to get samples to see those interesting effects. Can we have well isolated a single band and a much more robust correlation physics? So some of us look into different materials. Those monolayer semiconductors, particularly from the transition metal dichalcogenide group, so they are semiconductor with finite gap, and perhaps you can fulfill some of those requirements. And hopefully at the end of the talk, I will be able to convince you that this is really a good platform for strong correlation. So remember on the first day, Professor Ali Yazdani mentioned that there are 2 periods for contemporary condensed matter physics, topology, and correlation. So I think graphene really is an excellent example for topology and may also for correlation, but this semiconductor Moire superlattices are pretty rich in terms of strong correlation. Okay, so we have heard a few lectures on optical properties of transition metal dichalcogenides. I'm not going to elaborate too much. I just have a couple of slides to quickly remind you the basic properties, okay? So what I'm showing you here is a monolayer of, we call it TMD, So in the middle, you have moly or tungsten metal atoms, and you have chalcogenides on top and the bottom in this trigonoprismatic structure. And if you look down from top, it forms this honeycomb structure, pretty much just like a graphene. And about a decade ago, we and our collaborators discovered that in the monolayer limit, this class of material becomes direct bandgap semiconductor. And in the bulk form, they are indirect bandgap semiconductors, by the way. The gap occur at the K and the K prime point. So what I'm showing here is the simplified electronic band structure of this material near the band edge. So the gap here is about a couple of EV. And the material has very strong spin orbit coupling because of the heavy metal. So the conduction and the valence bands are split. they have like spin up and spin down. And this splitting energy in the conduction band is on the order of tens of millieV, and for the valence band is hundreds of millieV. And the effective mass for both the electron and hole is around half free electron mass. And because the time reversal symmetry is reserved, so if you change from momentum k to k prime, which is negative k, the spin also flips. So spin and the valley are locked in this material. So if you look at each, they have 2 degrees of freedom, spin valley degree of freedom. The monolayer semiconductor interacts very strongly with light. And this is a spectrum of monolayer absorption. And you can see very strong peaks. And and this is due to electron-hole interaction, and they form excitons. Otherwise you would just see some kind of a step-like transition due to joint density of states. So this peak, can be almost like 10%. So each monolayer can absorb at the resonance at 10% of a photon. And that you will see a little bit later in the talk gives us a lot of sensitivity if you want to probe the system. And that the 2 peaks, corresponds to a transition, between the spin split bands. So we'll be mostly focused on the lowest energy one. People often call it A exciton. And I'm showing here is the lowest exciton states, and there will be also, 2s for this lowest transition, 3s, and so on and so forth, when your sample is better. And this is from about 10 years ago. And now the sample quality is so good that this peak width actually is pretty much just limited by the radiative lifetime on the order of a few millieV. Then you can resolve the high energy states much better. The other thing I want to remind you is the optical selection rules. The spin valley properties, if you add up all the angular momentum, and you can work out that the 2 valleys couple exclusively to either left or right-handed light. Okay, so now we are going to follow Pavlov's first step and try to stack them, okay? I would just focus on one example, but there are many different pairs you can come up with. So this example is given for tungsten selenide and tungsten sulfide. And let's say we stack them with 0 twist angle. So those 2 materials have a relatively large lattice mismatch, about 4%. So if you look at the Moire period, which is given by this simple relationship, and A is the lattice constant, which is on the order of ½ nanometer. So this is a large, when the twisted angle is theta is small, so it's mainly determined by the lattice mismatch. So for 4%, we get the lattice period on the order of 8 nanometers. And when the twisted angle is relatively small, you can see that the Moire period doesn't change much. And that gives you this wide tuning range, okay? And this pair is known to have type 2 band alignment. That just means, the conduction and the valence band of the 2 materials are stacked like this, okay? So the lowest conduction band lies in WS2 layer, and the highest valence band lies in this WSE2 layer, okay? So now we have Moire superlattice. You can think about Bragg reflection. Then you can fold the bands. And I'm only drawing for one valence band, and I'm not drawing for a conduction band. So you can imagine that happens for all the bands, okay? So if you fold, for example, this top valence band, and you get mini Brillouin zone, like mini bands like this, okay? And when you tune the Fermi energy, you know, you can sweep doping through this band, or you can even go to other bands. And if you go to the other direction, electron will go to WS2 layer. And again, you're going to have those mini bands because of Moire superlattice. Okay, so now I would just like to give you kind of a quick comparison between twisted bilayer graphene and the TMD heterobilayer. So in twisted bilayer graphene, we have sublattice symmetry, two-fold degeneracy, layer symmetry, that's another two-fold, and we also have spin degeneracy. So altogether, each band is 8-fold degenerate. So that means you need to fill 8 electrons or 8 holes per Moire site to fill one band. The story is simpler in TMD heterobilayer because the sublattice symmetry now is broken. So this is gone. The 2 layers are different. So this is also gone. So what's left is only 2 double degeneracy, and that's the spin valley degeneracy. So we need 2 electrons or 2 holes to fill one Moire band. So later I'm going to use a filling factor, and that filling factor is for how many electrons per Moire site. So for example, filling factor equals 2, that means, you know, 2 electrons per Moire site, and that's full filling for one Moire band. Okay, so and this is a theoretical work from Chen-Fen Wu and Alan McDonough a couple of years ago. So what they did in this paper is to you know, point out that the TMD heterobilayer can be described by this very simple Hubbard model. You have an isolated band, and then you have spin valley degree of freedom, and it can be projected to this model with only 2 parameters. One is this U, which is on-site repulsion energy. So how much energy you need to pay to put 2 electrons at the same site. So here, this length scale is not the period, it's the size of the electron wave function. You can think about that. And this U is on the order of 10 to 100 millieV. And the T is the hopping parameter between the 2 neighboring sites. And for TMDs, depending on the twist angle, it's on the order of 1 to 10 millieV. And this T is pretty much the same as a bandwidth, you know. So for the triangular lattice, it's the bandwidth is 6 times of T. So this is actually quite remarkable. So why is this important? Okay, so we all know that the Hubbard model was, you know, one of the major models in strong correlation physics. It is thought to capture the essential physics of high temperature superconductors, magnetic insulators, and other complex quantum many-body ground states. So although the Hubbard model provides a greatly simplified representation of most real materials, it is nevertheless difficult to solve accurately, except in the one-dimensional case. So if we have a physical system that describes the Hubbard model in 2 or 3D and with some parameters widely tunable, we expect that this can be used as a simulator for to understand other classes of materials and phenomena. As I said, it's a difficult problem to solve. We have a pretty good understanding of what's going on in a few kind of limiting cases. So one of them is for half filling, when the band is half filled. And that's the case when we have one particle per lattice. So in this case, in order to create, charge carrying excitation, so in the absence of interaction, this is a metal because the band in the single particle picture is half filled band. So we all know that. But when you include the interaction to create charge carrying excitation, you gain energy of T, that's hopping energy, but you have to pay the penalty of U, right? So when the two parameter, the ratio reaches some critical value, it's not energetically favorable to create charge carrying excitation. In other words, the system stops becoming a metal. So this is the point when we have metal to insulator transition, and the band actually splits into two, the top and the lower Moire band, and separated by this parameter U. The other thing we also know pretty well is the magnetism of Moire insulators in the limit of a large U over T. So in this limit, you can think of this Hamiltonian, this is unperturbed, and this T, is a small perturbation. And to figure out, whether parallel spin or anti-parallel spin gives you a lower energy, you can think of this super exchange process. It's like this, electron hops over and hops back. So this is described by second order perturbation theory. So in this case, this is forbidden, but in this case, you can work out that, this state has a lower energy, and it's lower by T squared over U. So from this simple perturbation theory analysis, we also know Moire insulators are antiferromagnetic in the ground state, and the super exchange energy is on the order of T squared over U. We are considering a triangular lattice, and this is a little bit more complicated than, for example, square lattice, for antiferromagnetic coupling. So we want to align this being anti-parallel. So in the square lattice, it's very clear how to do it. But in the triangular lattice, if you put those two spins anti-parallel, then what are you going to do with this one? Okay. So the lattice is frustrated. You have multitude of competing states, and this gives extra complication. So so far I've only talked about filling factor equals 1 half filling. But what happens if you dope Moire insulator away from half filling? And you can easily imagine the problem becomes very complicated. So have a physical system, as I said before, that can realize Hubbard model is really helpful. So we can tune the filling factor by changing electrostatic gating. And this interlayer hopping depends pretty much exponentially on the twisted angle. So you can tune U over T, or you can come up with screening scheme and tune U over T. So in principle, you can tune U over T over a very large range, and also the filling factor. So now let me get to the experimental aspect. And I first focus on nu equals 1 case. I think I need to speed up a little bit. Here's our device structure. We have the twisted or untwisted 0 degree, heterobilayer, and we have hexagonal boron nitride and field layer graphene as top and bottom gate. And this is how device looks like. The fabrication is very similar. We followed the steps people use to fabricate graphene. The only complication here, we need to align those 2 different materials. For twisted bilayer, you can use the same layer and tear into 2 and put on top. But here we need to determine the crystallographic orientation of those materials first. And this can be done by second harmonic generation. Monolayer has broken inversion symmetry, and you get this beautiful 6-fold symmetry when you look at the second harmonic. From this, you can determine the high symmetry axis of the crystal, and then you can bring 2 crystals together and stack them. And after you finish, you can look at the overlap the area and do the second harmonic generation again. If they are 60 degrees aligned, the emission dipole from the 2 different layers are anti-parallel, so they destructively interfere, so you get almost nothing. And if it's a 0 degree, you get a large enhancement. So we can do this with accuracy on the order of ½ degree. Okay, so now let's take a look at some transport results. Resistance as a function of a filling factor and at different temperatures. Okay, so at low temperature, you can see that there are 2 very pronounced peaks showing up. Unfortunately, at low temperature, low doping density, the contact resistance becomes very big. So we cannot get useful information out of this doping range. So resistance peak at a filling factor 1 and 2. So filling factor 2 showing insulating behavior is quite understandable because, even in the single particle picture, now we have band insulator. At half filling, the physics is pretty much as what we discussed. In the limit of a large U over T, the interaction split this band into up and lower mod band, and it's separated by this U Coulomb gap. And that's why we see a large resistance peak. And from the temperature dependence, we can also estimate how large this U is. It's a little bit underestimated. So in this case, it's 20 millieV. Next, the ground and the low energy excited state, the MOS state, are determined by interactions between the localized magnetic moments that survive charge localization. So it's really important to look into the magnetic interactions. So how do we do that? I will first, before I explain the experiment, I first would like to remind you of the basic idea behind the magnetic susceptibility measurement. So for localized non-interacting spins, it's described by Curie's law. You know, if you apply a magnetic field, you polarize those localized spins. And energy can be described by the product of the two, and you can find a magnetization at a finite temperature, and find the susceptibility as the ratio of 2 in the limit when magnetic field goes to 0. For localized non-interacting spin, we know that susceptibility goes like 1/T. So now if we include the interaction energy is on the order of J, this picture can be modified. So now the field that each localized spin feels is not just the applied magnetic field, also has the field that comes from the other spins. And this is called the molecular field, or sometimes also called the Weiss field. So if you take this into account, you can modify the magnetization as function of temperature and come up with this Curie-Weiss law. Susceptibility goes like constant divided by T minus some Weiss constant, which is on the order of this magnetic interaction J. So this is how magnetic susceptibility looks like as a function of temperature from our solid state textbook. This is for paramagnetism, and for ferromagnetism, you know, above the Curie temperature, it follows this and then diverges at the Curie temperature. And for antiferromagnets, you know, you above the neo temperature, you have this 1/T minus theta dependence. And then if you ignore this and keep going, extrapolate, it diverges at this constant, now is negative. So it's a little bit cleaner if you look at the 1/susceptibility, and they all follow the linear dependence, right, as function of temperature. So for paramagnetism, you know, the line, if you extract from high temperature to low temperature, goes to 0. And for ferromagnetism goes to some positive number, and the antiferromagnetism goes to negative temperature. So in one word, in one sentence, you know, if you look at the high temperature behavior and extrapolate and looking at those constants, you'll be able to tell about the nature of the interaction. And this is exactly what we did. So the question is, you know, as I said, yeah, positive is ferromagnetic, and negative is antiferromagnetic. So the question is, how do you measure the susceptibility of about 10,000 spins embedded in a large magnetic background? And this is a place where optics comes into play, because we can tune the light wavelength into resonance with this exciton resonance, for example, in this layer. And this can be done by a simple, for example, reflection measurements. And we already know that the spin valley degree of freedom, right? And we can measure helicity resolve the refraction contrast spectrum of this lowest energy exciton as function of outer plane magnetic field. And the field is known to break the valley degeneracy, and each Henderson light couples to only one of the valleys. So this is the case when filling is 0 Tesla, and then if you apply 2 Tesla, you can see the 2 peaks split. So there's a question here from Maximilian Koch. Is there a problem to go to a larger Moire period by using a structure like MOSE2, WSE2, where the Moire wavelength is about 100 nanometers. So the answer, a short answer is no. There is no problem to go to larger Moire period. One of the reasons why we pick this pair is because the interaction is very strong. You get a large Moire potential. So if you want to follow up on this, we can talk about this at the end. Okay. So so you can look at this splitting, the Zeeman splitting, right? It's due to two contributions. One is the applied magnetic field, right? And the other one is the effect of this localized spins, magnetization. So by analyze this, we should be able to figure out the magnetization of this localized spins and also the susceptibility. Okay, so here just a series of measurements at different fields. And here is Zeeman splitting as a function of magnetic field. And then you can look at the slope near zero field to get G factor. And that G factor is proportional to the susceptibility of this localized moments. And the G0 here is the bare exciton response in the absence of those localized moments. So we did a temperature dependence measurement. So the magnetic susceptibility now as a function of temperature, and then you can fit to the Curie-Weiss dependence, and this is a 1 over chi. You know, it's the same thing. We got the Weiss constant on the order of -1 Kelvin. So does this make sense? We can put this back into the super exchange I discussed earlier for Mott insulator. So this magnetic interaction energy is on the order of T squared over U, right? And we already know U is on the order of 20 millieV from the temperature dependence of the resistance peak. Theta or J now is on the order of 1 Kelvin. We can get T is on the order of 1 millieV, and then U over T is on the order of 20. So this is in the you know, strongly correlated limit, and this this parameter T and U sort of agree with Wu and McDonald paper. So it seems to make sense. And then the next thing, of course, we did is to sweep away from half filling and look at how the Curie-Weiss temperature change, this and that. So let me go to that data. So this is the magnetic phase diagram we obtained using this technique as a function of filling. So the black dots are the G factors. You can think of them as magnetic susceptibility, and you know, can be very large. Those dashed lines are just the guides to the eye. It looks like, you know, it tries to diverge or at those 2 points. On the right-hand side, we plot the extracted Weiss constant. So it's negative value. So near filling factor 1.2, it's you know, 0-ish, and for lower filling, this parameter is positive, and that means this is antiferromagnetic. And on the larger filling site, this is a slightly negative theta is slightly negative, and that means this is it's a weak ferromagnetic. So based on this, we can make a conclusion that on this side, it's antiferromagnetic, and on this side, it's either paramagnetic or weak ferromagnetic. Unfortunately, the signal to noise ratio of our measurement, we cannot, make a good conclusion, very definite conclusion at this point. So and then something interesting perhaps is happening at this point. Is this some kind of a quantum phase transition or what? So this is just the beginning of it. That's something I would like to emphasize. It just shows that the system is strongly correlated, and we have techniques that can probe it. Lots of interesting things going on. If you look at it somewhere here, the susceptibility drops. What's happening? This strange shape. So lots of things still not well understood, but hopefully, this will inspire future theoretical and experimental investigations. So we have a question here. What is the contribution of the orbit magnetic susceptibility to the splitting? So this refers to, so right here. I went through the introduction of TMDs very quickly. So in those TMDs, when we talk about the optical selection rule, so you can look at this angular momentum, right? So you can have contribution from the orbitals, so those are d orbitals, and you can have spin. You can also have valley, which is the orbital magnetic contribution to the exciton. So for exciton, because it's electron hole, so you need to put the two contributions together. So for example, the spin contribution cancel for exciton, and the orbital, they have different d orbitals, so you can put this together. So the bottom line is, if we don't have those those localized moment spins, the G factor for exciton is on the order of -4, and that's the combined contribution from the orbital magnetic, the orbital magnetic moment, and also the atomic orbitals. So I hope I answered your question, Oscar. If you have more to follow up, we can discuss at the end of the talk. Okay. Okay. So I would like to return to this picture a little bit. So I presented this transport result, to show that we have a resistant peak at half filling, or nu equals 1. But unlike those beautiful transport work from graphene, we actually suffer quite a lot, especially at low temperature for low filling factors. And that's because of the contact. And it's sort of intrinsic because we are dealing with large gap, with semiconductors. So an alternative to study this is to look at optics, although people in the community are working very hard to solve or improve the contact issue. And there has been some progress, but I would like to talk about, how we can use optics, to do some of the measurements as an alternative. So can we see a signature of Mott insuline state by looking at optics? So this is a counterplot of the fundamental exciton in WSC2 as function of doping. This is nu equals 0, half filling, full filling. Okay. So unlike in single monolayer, you know, the exciton will sort of quickly lose its oscillator strength as soon as you dope it. But here it keeps going a little bit longer. And you can also see some kind of a modulations, right? And this plot, we show the peak amplitude for the reflectance as a function of filling. And you can clearly see that there is increased reflectivity at full filling and half filling. And you know, the way naively you can understand this is, you know, those are insulating states, so excitons are screened less, and that's why they have higher oscillator strength. But to have a full picture of this, you know, we need to understand the many-body interaction in the system better. And if you have very sharp eyes, you can also say, hey, you know, look here and here, you have some also enhanced absorption. So what are those guys? So the Fengwang group at Berkeley came up with this very clever way to measure those things a little bit better. So instead of looking at the exciton response from the same place when you dope, they have look at the optical response from neighboring layer connected, but you know, the charging happening in one area and the probe happens in the other area. So you look at charge flow in and out this way. And they were able to optically measure the capacitance and the resistance. And they saw, of course, you know, this peak in the resistance channel, for example, at full half filling. And that those two bumps, you know, at 1/3 and 2/3 of nu are assigned to charge order states. So we can see that, you know, the charge holes here try to avoid not only double occupancy in one site, they also try to avoid adjacent sites. So this tells us that not just the on-site Coulomb repulsion is important, actually the interaction between, you know, neighbors also very important, and the long-range Coulomb interaction plays role because it's larger or comparable to T. So now I would like to switch gear, talk about charge order states at fractional filling. And from those early experiments, we've already seen that, you know, V is important, you cannot ignore it. And this is because, you know, gate separation is much bigger than the Moire period, so you cannot screen out those V's very well. And the correct model to describe this, of course, you have to include the long-range Coulomb. And in the case of our system, you know, U is much bigger than V and T, so you can pretty much forget about U for fractional fillings. So the question is, how do we come up with better way, more sensitive way to, you know, probe those states? So this is the approach we have tried. And it utilized this property of excitons in a monolayer of semiconductor. And I've already mentioned, you know, exciton interaction is very strong in this material. They form bond state and looks like a hydrogen atom, two-dimensional hydrogen atom with 1/r potential. So they have, you know, series of Reber states, you know, 1s, 2s, and so on and so forth. And 1s is strongly bound. The bore radius is on the order of nanometer, and the 2s is on the order of 5-ish, you know, and the 3s would be bigger. So if that's the case, you know, if I put this layer next to somebody else, The field lines, you know, because it goes out of this material, can feel the screening effect or dielectric function of the layer sort of adjacent to it. And this is a simple, you know, a solution from 2D hydrogen atom. The binding energy goes as 1 over dielectric constant square. So if we put a metallic layer, in other words, compressible system next to it, you're going to screen this a lot, right? So the binding energy should be small and oscillator strength will also be small. If you put an insulating material, in other words, incompressible system next to it, the binding energy is large, reduce the less, so, and the oscillator strength is big. So by looking at those excitons, we should be able to tell what you put next to it. And this is the device schematic. So here is our sensor layer. And to electronically separate from the system we want to measure, we put HBN spacer of nanometer or that order. And then this is the sample layer, and we can have gates to charge, dope this sample layer. So here is a tester system. We have monolayer of a WS2 as a material that we can change doping, and then we look at the response of the sensor, you know, to get an idea. So let's look at the right panel first. So this is the optical refraction contrast from monolayer of a WSC2S2 directly. And this dashed line is the voltage that you're putting charge into it. So below, it's insulating, you know, the Fermi energy is in the gap. And as soon as you introduce charge, in this case electron, into WS2 layer, the neutral exciton loses its oscillator strength, blue shifts, as you heard Imamogu's talk, you know, as repulsive polaron, and at the same time another redshift branch appears, and this is the attractive polaron, and sometimes we call it a trion or charged exciton. So this is pretty well known for isolated monolayer. Let's take a look at the sensor layer response. So the 1s exciton doesn't change at all because we put doping into WS2 layer, and this, I mentioned, you know, the 1s exciton is tightly bound, it's small, so it does not feel what's going on in the sample layer, which is nanometers away from it. But the 2s exciton changes dramatically. It sort of follows what's going on in WS2. You know, you have this shift to lower energy, and then you can also see a 3s, you know, and higher 3s pretty much. And with doping in the sample layer, this disappears also. Okay. So here we have a very good signature of what's going on in the sample layer. If you follow the intensity of the 2s state and also the energy 2s state, you know, as soon as the sample changes from insulating to metallic, from incompressible to compressible, you see a redshift in the 2s energy and also loss of oscillator strength. So I have a question here. How do you measure reflectance selectively from sample and the sensor layers? The answer is that we don't need to. If you look at the x-axis, you know, they all occur at different energies. So spectrally, they are separate. So you don't need to do anything fancy, just to do your regular reflectance measurements, and they are separate into different energies. Okay, so now let's apply this technique to our Moire system. And this is what we saw. So what I'm showing here is the 2S state from the sensor layer, and as a function of gate. And what the gate does is only changing the doping in the Moire system, okay? And the positive gate voltage dopes electron into WS2, and the negative voltage dopes a hole into WSE2, okay? So you see the change of those peaks or candle-like objects. So this tells us the 2S exciton energy. So for example, the higher 2S energy means the material is more insulating, right? And the darker the color, the blue, that means the oscillator strength is bigger. So the peak at the voltage equals 0 corresponds to Fermi level in the middle of the gap. And this is the largest band gap of the system. And this is a very good insulator. And we also see peak, you know, at nu equals 1 and nu equals 2, and this is the mod insulator, and this is the band insulator we've already talked about. And if you look at this bunch, and you see, you know, here, and that's 1/3 and 2/3. And if you look more carefully, there are a bunch of other states, and I label all the ones that we've been able to identify. So while you are looking at this panel, I'll try to answer one question, okay? So the question from Wei Yang, what is the thickness of the HBN spacer for effective sensing? Okay, so I mentioned that the ball radius of 2S is on the order of 5 nanometer. So as long as you are below this, you have sensitivity. So in this particular experiment, it's 1 point something nanometer, and you know, you don't want electronic coupling, so that's not too thin but not too thick. Okay, so you can imagine we can do this experiment at different temperature, and then you can watch, you know, the peaks disappear one after another, and then determine their ordering temperature. And this is a summary of what we saw for those states. Different states have different ordering temperature, and we collaborate with Vice Alsar, you know, who did classical Monte Carlo simulation for example, the electron side, and those are the patterns, you know, corresponding to those states. So I don't have much time left, so I would like to finish up the discussion. So anyway, so by looking at this, we can also tell there are some quantum effects. So one kind of a simple thing to look at is this nu equals to half, right? So you can think of this as either half filled lattice, you know, or half empty lattice. So this filled and empty are symmetric, so they are equivalent. So if the kinetic energy or quantum fluctuations are not important, then we expect 1/3 and 2/3 to be identical, 1/4 and 3/4 to be identical, and so on and so forth, right? But we see that they are not quite identical, especially on the whole doping side, and that tells us that the quantum fluctuations are important, you know, especially for the whole side. You can also look at the filling factor larger than 1. They are generally weaker, you know. So that also tells us that kinetic energy is important because, you know, the higher the filling, you know, the smaller Coulomb over kinetic energy ratio. So that's kind of one comment I would like to make. The nature of those states, you know, we already look at 1/3 and 2/3, and those are likely Wigner crystal states, and those weaker ones likely are, you know, charge density waves. But, you know, there are still a lot of things to learn, and I believe, you know, this is just again the beginning of it, you know. Just to give you one example, you know, if you look at those patterns, you say, well, you know, 1/3, this and that, you know, they sort of still have this rotational symmetry, right? But if you look at particular half, they form chains, right? So the rotational symmetry is broken, and then this likely give you different properties. So then the question is, you know, how do you probe this, you know, and so on and so forth. So I hope, you know, this gives us kind of a hint that the interaction effects are very strong in this system, and it's a super rich. So I would like to stop here and put up my summary. And there are some questions. I'll get to the question after I finish my summary, okay? So I hope that I have convinced you that semiconductor Moire system provides a good platform to study a strong correlation. And this, we've seen one example that it's a good, reasonably good realization of the triangular Hubbard model, and perhaps we can use this as a quantum simulator. The ground state half filling is an antiferromagnetic Moire insulator, and this is consistent with expectation in the limit of large U over T. The long-range Coulomb interaction also important in this system, and you know, that tells us U is also bigger than T, and for some states and for some maybe comparable. So if you can tune those parameters, lots of interesting things are expected. And we have seen abundance of charge order states at the fractional fillings. I believe those are not seen in graphene at the fractional fillings. And as I said, you know, system is very rich, and we need new techniques to look at them, and of course also theoretical support to understand what's going on in the system. So I would like to answer this question. This question is from Shen Fan. Does the BN spacer affect the Moire effect for WS2, WSE2? The short answer is no. And you know, so the HBN is random. HBN has the lattice mismatch between HBN and the TMDs is huge. So we don't expect any Moire, you know, effect also. Next question, is it possible to perform some kind of micro diffraction experiments to probe the stripe faces? I think that's a very good suggestion. And I you know, I think it is possible, and something like that probably should be done. The kind of a concern is that, you know, we need to be careful not to disturb those states too much. But yeah, that's something one should think about. Okay. one more question. Do you see any anomalous G factor for fractional filling effect for WS2 layer in the electron doping regime? The short answer is that we have not looked at that.
I see somebody had the hand raised, but now I don't see it anymore. Yes, somebody. Max, you are allowed to talk.
Yeah. Thank you for the talk. I was wondering, at the beginning you talked about the Hubbard model simulator. If we want to have like an efficient Hubbard model simulation with Moire, with the Moire pattern, we would need to efficiently tune the interaction strength and hopping strength. From the talk, I think I got that those two parameters are basically defined by the Moire wavelength. Is there another way to tune those parameters? Because that would involve making an own structure every time you want to do different regimes.
Okay, so that's an excellent question, you know, and I share your thought, you know. So changing the twisting angle to tune the U over T is not ideal because, you know, we don't want to make a new structure every time. So electrical tuning, something like that will be an ideal, you know, for this type of experiment. So things like tuning the screening, and there are other, you know, there are other ways to do that. And that's something, you know, people in the community are actively working on. And yeah, so I probably shouldn't say too much about that.
Okay.
So there are ways, you know, soon you probably see papers out.
Okay, thank you.
Okay. If you want to ask a question, please type it in the Q&A box or raise your hand. I don't see any more.
So, Jie,
Yeah.
I think I missed your answer to a previous question. What was the spacer for the sensor layer?
Oh, okay.
Is it HBN thickness?
Yeah. So so the HBN electronically separate the sensor and the system you want to probe. But you don't want the HBN to be too thick because you know, you want to still within the exciton ball radius. And for the 2S state, we're talking about something like a 5 nanometer. So you know, so as long as you are within that bulk number, you are fine. So the example I showed here is something on the order of 1.3 nanometer.
But shouldn't you be screening then the V, you know, because the sensor layer is very close to the actual Moire heterostructure? Or did you notice an effect depending on the charge density on the sensor layer? You know what I mean?
Okay. So I did not make it very clear. Okay. So the sensor layer is always neutral.
Okay.
Yeah. Sensor layer.
Do you have an independent gate controlling the charge density in the sensor layer?
Well, so this is somewhat lucky in terms of arrangement. So we use the sensor layer is also WSE2. And the system we look at is WSE2 and a WS2, right? So because of the Moire potential, the WSE2 in the sample layer has a smaller gap because of Moire potential. And the WSE2 in the sensor has a larger gap. You can think about that. So when you when you gate, you know, the moiré system, the charge goes into your moiré, and it leaves the sensor layer charge neutral. But you can come up with gates to control doping density in the sensor layer as well. I don't see how, why this cannot be done if you need to.
Okay, thank you.
Okay, I think there's one more in the Q&A.
Do we have any expectation for the magnetism of the fractional field correlated states? Yes, you are doing my project. Yeah, so so we are studying magnetism of some of the fractional field correlated states, and it turns out that it's very rich. We don't have a completed story yet, but more is to come.
Okay, so I think we need to conclude. I have to really say that it was extremely wonderful to see these new results, very impressive results. Also the, what is it called? The candle tree diagram is very beautiful. And I shared that comment with Pablo, who made that comment to me privately. So we like to see this work coming out, but come back for our next talk at our next workshop.
Thank you for your invitation.
And, yeah, on behalf of all the attendees, I give you a big applause. And yeah, thank you again. Bye-bye.
Bye.
Okay, thank you very much. Thank you all. This is the last session for today, so I'm gonna end the meeting now, and I will see you tomorrow.
See you tomorrow.